Welcome to RISE Learning Machines seminars. Today, it's my pleasure to introduce Kyunghyun Cho from NYU. Kyunghyun has a PhD from Aalto University in Finland. He made his postdoc at Mila in Montreal. He's now an associate professor in the Silver Group at NYU, and he's been at FAIR, Facebook AI Research, between 2017 and 2020. Kyunghyun has made many important contributions to deep learning. Specifically, applied to natural language processing, including the gated recurrent unit and attention-based neural machine translation. Today, we're going to hear about characterizing and addressing the issue of oversmoothing in neural autoregressive sequence modeling. And for those of you who are interested or want to check it while you listen, there is an archive paper. With that said, I will hand over the screen sharing to you, Kyunghyun.
All right. So in fact, almost in the last minute, I actually created a new slide deck just a few days ago, and I thought it's going to be more fun to talk about it. So I'm not going to talk about the oversmoothing issue today, although I'll be happy to share the slide deck for the oversmoothing with you afterward. But rather, I'm going to focus a bit on the data augmentation for natural language processing. I'm very happy to be here, and hopefully next time I'll be there in person as well. So to talk about the data augmentation, we need to first talk about a bit of an intuition as well as the science behind data augmentation, and then that is what we often refer to as manifold assumption. According to the manifold assumption, the high dimensional data lie roughly on a low dimensional manifold. What it says is that when we think about the data that we work with, you can imagine images, you can imagine speech, you can imagine natural language, you can imagine any kind of tabular data as well. And almost everything often tends to be in a space where the possibility is very, very high, or the number of possibilities is very, very high. So sometimes it shows up as the very large, let's say, hypervolume, which tends to grow exponentially with respect to the dimensions, or sometimes it shows up as a combinatorial nature, like in language. And when you think about this very large space, what you realize is that in fact, much of the space is not occupied by a meaningful data. So in the case of images, you can imagine that what would an image created by sampling each of the pixel or pixels intensity randomly, uniform randomly, between a minimum and maximum intensity allowed. If you sample them randomly without any kind of strong correlation among them, you will never get any image that looks like a real image. What that means is that all this data that is meaningful is somehow in a very low dimensional space, or the subspace within a large space. And then we have known this for many, many years, and then using or exploiting or benefit from this manifold has been a key technique in order to improve our machine learning algorithms. So let's keep this in our mind for now. And going back to the very, very basic of machine learning, what we often do, or what we really want to do, is what so-called expected risk minimization. So we're going to look at all possible points in the entire space, and then for each of the point, we're going to look at how probable that is under this unknown, but the true data distribution. So if the point is highly likely, it's going to be considered more important when we compute this expected risk. And then that weight or that probability is multiplied with the loss computed at that point. And then this loss tells us what is the discrepancy between what our model thinks and then what the associated true label Y is. And then we try to minimize this expected loss over the entire data manifold. Unfortunately, we cannot really do it or minimize it directly because, first of all, we don't have access to this true data distribution. And even if we did, it's not going to be tractable to consider all possible input-output pairs. So instead, we rely on empirical risk minimization, where instead of using the all possible or considering all possible input-output pairs, we're going to consider only a finite number of input-output pairs that are provided as part of what we call data or the training data. And then in this training data, all these examples or the input-output pairs are assumed to have been sampled from the true data distribution. And we often have the regularizer, omega, written as omega in this slide, that minimizes the complexity of this function f or the classifier f that we're trying to train here. Now, let's look at a slightly different way to write it. We can rewrite it as if we're considering all possible points in this input space still. But then we're going to introduce a delta function that says that we are only considering the points that are right on the training examples only. And what we can see is that that is going to tell us that instead of the actual data manifold, over which the probability of under the true data distribution is high, we are only considering a small number of, or the collection of points in this entire space. And then this space is really large, right? So of course, what you imagine is that simply look at the training example often does not tell us too much about the data manifold. Instead, what we can do is we can try to incorporate the neighborhood structure. And then that's what we often refer to as, or was proposed as, Vicinal risk minimization in 2001. Now, instead of looking at a single point, we're going to look at the neighborhood or the vicinity or the points in the vicinity of each and every training example. And then to do so, we need to have what we call a local distribution for each of the training examples we have. And then this local distribution tells us what constitutes as a vicinity of this training example. And by considering a collection of these vicinities of the training examples, now we can get a better sense of what is the true data manifold that we need to consider. And this local distribution, we often separate it into the local distribution in the input space and the local distribution in the output space. And the reason why we often do so is because it's not easy for us to think about how to think of the local structure that considers the input and output jointly all together. However, we can do so better for the input separately, and then given that example in the vicinity, what the corresponding y should be. And we're going to talk about that quite extensively over the rest of the talk. So what is this local data manifold? Let's look at the input space first. So it's going to be p local x prime given x. So x is one of the training data points on the input space, and then x prime is the neighborhood. And then we try to look at how likely each of the neighborhood is given this training input x. And this local data manifold is often designed based on domain knowledge. Of course, we can automatically learn from abundant unlabeled examples. That's what we're going to look at. But if we know about the actual problem and then if we know about the domain, we can always come up with some reasonable, approximate way to characterize this local data manifold using our knowledge of the problem itself. And then by capturing this local data manifold, we can now collectively characterize the entire data manifold as well, as you see on the right side of the slide here. So we have 5 data points. For each data point, we know what the local distribution is. And then by looking at this collection or the mixture of all these local distribution along the training example, now we can now see what the entire data manifold looks like. It's a very cartoonish, let's say, view, but you can imagine that if we have a good idea of what this local distribution or the local data manifold should be, then we should get a better and better sense of what the entire data manifold is as the number of the training examples goes up. Now, on the other hand, if you think about the local distribution in the output space, it's a bit difficult. Even domain knowledge doesn't help there. Why is that? Because it's largely equivalent to solving the true problem itself, that is trying to estimate the true P of y given x. If we knew this, we wouldn't even need the vicinal risk minimization because we just actually have solved the problem. So we really don't know how to design these output spaces local distribution. And the only thing that we can impose is often smoothness. What that means, in fact, is that we simply say that the distribution over the output, given the x, the original training input, x prime, the example from the vicinity or the neighborhood of the x, and the associated label y, so associated with the original training input x, is simply to say that the y prime has to be identical to y. But interesting thing is, by doing so, we actually introduce a high level of smoothness into the target distribution. As you see here, if we look at all these vicinities of the training examples, and then if we impose that within this neighborhood, given any training example, the labels of the examples are all same, what happens is we automatically impose the smoothness, at least over this data manifold. And that results, of course, yes, please.
Yes, hey, my name is Edwin, and I'm a researcher and PhD student here at ri.se. And I think this is really interesting. And maybe you will get to that, but I wonder,
okay,
the dimensionality of the manifold that you talk about. I would guess that that's important for the analysis you're talking about. And I wonder if you could elaborate a bit, if the same things that you talk about here, does it hold in high dimensions, or do you need to tackle that differently? Like you had images, for example,
right,
very, very high dimensional, perhaps images are sparse dimension.
Right, yeah, so this is a really great question, because the smoothness so a lot of the, let's say, cartoons that I'm drawing, like in this slide as well as this slide, and then all your slides as well, often are in a very limited dimension, often 1 or 2 dimensions. Now, how much of the intuition or the analysis that we do in this low dimensional space correspond to or the generalize to a high dimensional space is not trivial, right? That's perfectly true. Now, what we do is, instead of actually characterizing or identifying this data manifold explicitly, we're going to actually rely on machine learning, in particular the unsupervised learning, to characterize this local data manifold automatically. And then that's the kind of, let's say, point we're going to get to. Now, still, the figuring out the true dimension of this low dimensional, let's say, data manifold is kind of impossible, because that's same as having access to the true underlying data distribution. However, what we see is that we can check whether this data manifold that has been captured by the unsupervised learning is meaningful by looking at how we can use it, and then whether we get the expected improvements on the downstream tasks that are going to utilize or the better exploit the availability of this data manifold. And I'll get to that one a bit later. Yes.
Okay, thank you. That's really interesting. Thanks for the answer.
Yes. So, yeah, and then one of the reasons why we want to impose, or that we often impose, this smoothness, and then how the vicinal risk minimization is supposed to work, is because we expect such a smoother classifier to generalize better. And then it should generalize better along the data manifold represented by the training set D and their neighborhoods. And we're going to actually check, I'll come back to it at the very end of the talk, whether it is indeed true, and then whether this kind of expectation is reasonable in real world problems. Now, let's see how we can actually design this kind of local distribution. And then when it comes to, let's say, distributions, it's never easy to, in fact, come up with the analytical form or the distribution that has analytical form for computing the probability under that distribution. Instead, what we can do is simply to write a routine to draw a sample from it. So instead of being able to compute exactly the distribution or the probability that is P local, what we're going to do is we're going to simply write a routine that allows us to sample some, let's say, neighborhood point given any input data. At the end of the day, we rely heavily on stochastic optimization, and then this kind of way of sampling fits very well with the existing framework of the stochastic optimization. And in the case of the input, we know how to often do that. We're going to use the domain knowledge to introduce some kind of perturbation. Sorry about that. Perturbation that is going to preserve the semantics as closely as possible. We're going to look at some of the domain-specific examples. Now, on the other hand, output, so p local of y prime given x, x prime, and y is a bit less trivial. But as I said earlier, we're going to simply often set the y prime to be same as y. Or we can use the ideas coming out of the code training or the entropy minimization. And then these techniques correspond to more recently called pseudo labeling techniques. So we're going to use another classifier in order to label this x prime that is generated on the fly. And we often write this kind of, let's say, sampling routines by using how the problem looks like, essentially using our knowledge of what the problem is and then what kind of problem is being solved. And it's very, very useful for certain domains, such as computer vision, speech, and others, where we have studied very extensively, where the we is the collective we over the past, let's say, century or so, to see what are the equivariances or the invariances that we need to encode in order to solve a problem better. Unfortunately, such domain-specific data augmentation is often not applicable nor suitable for other domains such as natural language. And in these domains, we need domain-agnostic data augmentation for a broad set of data augmentation methods. And that's going to be the key, let's say, main part of this talk. But let's just look at a few domain-specific methods. One of the biggest success stories of modern deep learning is AlexNet from Krzyzewski, Suskever, and Jeff Hinton from 2012. And in that particular paper, the importance of domain-specific data augmentation was emphasized with more than half a page dedicated to domain-specific data augmentation techniques that they used. They did the random translation as well as the random horizontal reflection. And then they very explicitly state that without this scheme, their network suffered from substantial overfitting, not resulting in any good, reasonable, let's say, classifier that generalizes well. And they also use the pixel intensity alteration, which looks quite complicated, to be honest. However, which was really important to get the generalization error by 1% or over 1%, which is quite substantial in the case of the ImageNet and especially back in 2012. Now, this kind of, let's say, domain-specific augmentation for computer vision or the image processing or the object recognition has been pushed all the way. So there is one paper from 2019 by the Kubugel, and then they propose a method called rand-augment. They literally randomly select a series of augmentation or the transformation of an image coming out of the image transformation library in Python. And then they just apply randomly, a random series of transformations. And then they say that whatever we get out of this series of the randomly selected transformation is going to be an example from a neighborhood of the original image. Now, although I did say that the natural language is not the domain where it's easy nor possible to come up with a very high quality data augmentation that is specific to the particular domain, but that doesn't mean that people haven't tried. For instance, Wei and Zhu in 2019 proposed what they called as a easy data augmentation. I don't think it's easy at all, but still they called it a easy data augmentation, where they introduced data augmentation to the natural language processing by, let's say, replacing some of the words with synonyms, randomly inserting some of the words, randomly swapping the order of the words, and randomly dropping some of the words. All these are domain specific in a sense that of course, replacing some words with the synonyms are largely going to preserve the meaning of the entire sentence. Randomly inserting one or two words often do not break the meaning of the sentence, completely. It just makes it an ill-formed sentence. Random swap, random drop, all the same thing. Now, unfortunately, this method is not really satisfying as it jumps off the manifold. So we start from a well-formed sentence that is by definition on the manifold. By applying this easy data augmentation, almost always, except for some rare case of the synonym replacement only, the example kind of jumps off the manifold, and that's not what we want. We in fact want to stay in the data manifold so as to ensure that the classifier we train is going to be smooth or generalized better on the data manifold. So to do better, the few other people have since then proposed a so-called round-trip translation as a way to do the data augmentation. You're going to start from the original sentence, use a machine translation system to translate it into a target or the pivot language, and then we translate it back into the original language. And then what happens is that we often get a pretty well-formed paraphrase of the original sentence. And then it is paraphrased because we do either add some information or remove some information due to the fact that there is never going to be a perfect one-to-one match between two languages. But it's still not really satisfying, as it is largely supervised. So we're doing a supervised data augmentation, and also it's quite slow. Furthermore, we are going to be always limited by the choice of the pivot language as well, because the pivot language tells us what kind of paraphrases are going to be possible and what kind of paraphrases are going to be produced. So instead, we want to do a domain-agnostic data augmentation for natural language processing, and we took the first step in 2019 and 2020 by using masked language model for data augmentation in natural language processing. This was a collaboration with Nathan and Merzieh, both of whom are at MIT these days. So what would be the most, let's say, domain-agnostic data augmentation method is to simply add unstructured noise. But unfortunately, this is not really possible because it's quite limited. We can only add a small amount of noise while ensuring that perturbed version still continues to stay on the manifold. And then, if we add only a small amount of noise, that doesn't really help because, as it was pointed out earlier, that the space is large, training data set tends to be quite sparse, and if you only add a small amount of noise, there is almost no overlap between the neighborhoods of the two examples, which means that we are not really imposing much of the smoothness there. Instead, what we can do is to rely on the idea of the denoising as a way to characterize or to capture this data manifold. Already in 2010, Vicinal et al. From Montreal were able to show that the training a denoising autoencoder is an effective way to capture the data manifold and then explore this data manifold without jumping off this data manifold. And that was 2010, and now we are in 2022, so it's been more than 10 years, and we are in the era of masked language models. Everyone in natural language processing, as well as computer vision, as well as speech recognition, as well as whatever you can imagine, everyone uses masked language model as a way to pre-train or initialize the parameters of a large-scale classifiers that can be now fine-tuned with only a small number of examples and still generalize as well. So that has been a mainstream use. And in fact, you go to any of these leaderboard for the natural language understanding, and nowadays, even for computer vision, object recognition tests, you see that it's all about using different types of masked language model. But what we also know is that these masked language models, such as BERT, knows really about the word. That is, that it really knows about the plausible ways to reconstruct missing parts of the sentence. And then what that actually tells us is that if we start from a well-formed sentence, mask out some of the parts of the sentence, and then let the BERT reconstruct, that is a very, very effective way for us to sample from the neighborhood of any given text. And then this is because the BERT knows about the word as well as the syntax and semantics of any kind of sentence that we give. And this is equivalent to saying that the BERT or the masked language model samples from a local data manifold. So in other words, we never had to actually come up with a very domain-specific way to sample from this local data manifold, but we could actually train a denoising autoencoder and then let this denoising autoencoder sample from the neighborhood by starting from the point in the data manifold, corrupt it, and then trying to push it back onto the data manifold by doing a by the process of denoising. So in the SIMBA, the self-supervised manifold-based data augmentation, we start with the very well-trained mask language model. And then we're going to augment the training data set by taking one example, apply the corruption, and then given the corrupted examples, we feed it into the mask language model to reconstruct all those corrupted parts. And then those reconstructed examples are going to be introduced into the data set to form a larger training set. And we can always, as I said earlier, can use some kind of optional self-supervision to get a target label that is not identical to the existing labels in the training set. And we train the classifier using this augmented data set in order to make a classifier that's going to be smoother along the data manifold, so that it's going to generalize better along the data manifold. So we did some extensive experimentation on the text classification as well as machine translation, but I'm going to go through quickly what we did and what kind of improvement we see. And then we compared it against the easy data augmentation. We talked about it earlier. Unsupervised data augmentation, which is a name that has been used to describe this round-trip translation idea. And also the conditional BERT contextual augmentation, where the BERT or the mask language model is fine-tuned to generate sentences for each of the categories. And we tested, because we test this data augmentation method with the recurrent neural net or the LSTM classifier trained from scratch, convolutional network trained from scratch, as well as the Roberta, that is the mask language model we use in order to perform the data augmentation directly by fine-tuning it. And what is really interesting is that unlike many other methods, such as EDA, CBERT, and UDA, which often helps, but sometimes it also can fail quite miserably, the SIMBA that relies on a very well-trained mask language model never hurts the performance compared to the baseline where we did not use the data augmentation. That's quite important, because if it hurts, how are we going to use it? And the second thing is because it is an indication that all the examples that we generate do indeed lie on the data manifold, thereby making our classifier generalize well along this data manifold. On the other hand, if you use this kind of, let's say, manually designed, handcrafted domain-specific, let's say, data augmentation method, what happens is that unless we are being very, very careful, we may generate a lot of examples that are off the data manifold, effectively hurting the classifier's ability to generalize along the data manifold. And then data manifold is where all these test examples are going to be drawn from. And what we saw was that it didn't really matter how many training examples or the labeled training examples we had, as long as we have the very well-trained mask language model. And also we noticed that we don't really need too many augmented sentences per training example in order to get the boost in particular on the out-of-domain test set. Now, of course, there's a big question of whether this is really about the number of the samples or the effectiveness of the data augmentation, or just that the problems that we solved were too simple. There are much more experiments and results in the paper, but if you have any questions, do ask me anytime. But I'm going to go into the next, let's say, section where I think we have a very interesting idea here. Essentially, the question is, can we do better? And
I have one question before we go to the next thing. Really interesting. So if I understood you correctly, you did some type of data augmentation to a pre-trained language model. I wonder, would it make sense, or perhaps it's out of the scope for your paper, but to do that augmentation in order to train a language model instead? Because the language models are trained with one augmentation, you could say, which is the masked prediction. But could you add this in the training part to make it even better?
I see. Yeah, that's a very interesting question. So I didn't actually go into detail here about the denoising autoencoder, but one of the important things about denoising autoencoder or using denoising autoencoder to capture this data manifold is to actually use the corruption that is as unstructured or the domain agnostic as possible, because that is the way by which denoising is going to learn what is the valid direction of change that's going to stay on the manifold, and then what are the invalid directions that this denoising autoencoder needs to suppress. So in that sense, when we train a language model, in fact, we want to introduce a noise that's as unstructured as possible. In fact, what that means is that we probably need to use much more sophisticated, let's say, noise rather than just masking during training to be even more effective. In fact, in my other life, I am actually working as a senior director at the Generative, and then there we use denoising autoencoder quite, let's say, extensively in order to generate all those protein designs. And there we use the corruption that includes, let's say, insertion, swap, deletion, and various things that are going to change or to introduce a much higher level of noise to the input when we train it. So yes, we can do better. And I'm going to actually talk about whether we can train a model better for the purpose of data augmentation.
That's really interesting. Thank you. I would imagine that an interesting research question would be like define what is an optimal set of augmentations for a specific
Indeed.
task. Perhaps that is what you're
definitely doing. Definitely, yes. So if you can learn that, that's going to be awesome. Yes.
And I have similar question, but if it's if we want to noise it with some specific direction, like supervised, like in some cases we have some malicious part of the sentence and some part which is a normal part, like anomaly detection context. Can we do that thing in that sense?
So yes, so that's true. So then if I understood your question correctly, then can we do the data augmentation or perturb the training example with the let's say the context or the label in our mind, so that if we want to so the class
so
kind of specific data augmentation,
so
right?
In other words, we already have some tags for each of the token, and we know that some of the part is corruption. I mean, we has label for that, but we want to generate a new data, more augmented data, but have some good diversity of this. Yes.
Right. Yeah, so that's actually interesting. So so far, and then throughout this talk, I'm talking a lot about the data augmentation that is pretty much agnostic or the unaware of the labels or the categories. However, it is definitely possible to think of a way to introduce the label information in the middle as well. And in fact, in this kind of, let's say, non-local or the global augmentation, we can introduce the kind of, let's say, class-specific structures by using that information. But I'll get to that one. I think I'll be able to partly answer the question in this second section of the talk. All right, so let's go into the non-local global augmentation. So what we looked at, or what I meant by the local augmentation, was that this kind of perturbation is conditioned on a single example. On the other hand, we can build a global augmentation method where the perturbation is conditioned on a single example together with all the other labeled training examples. And this enables us to go much further away from any individual example, and also has a better potential, or thereby has a better potential for generalizing to faraway domains. And furthermore, it allows us to capture a larger portion of the data manifold because we now have a global view of what we mean by the data manifold. So then, what do we need? How are we actually going to build this very complicated global distribution? It turned out that it's not really easy at all. And then, in fact, domain-specific way doesn't work anymore. Because even for the domains that we know the structures or the problem structure very well, if we start looking at the multiple data points and then trying to figure out what is the right way to combine them, we are pretty much clueless. Very interestingly, already in 2017, Zhang et al. Proposed the idea of the mix-up. That is one way to do the non-local data augmentation. And then they show that we really don't need to think about all those data points in the entire data set. Instead, what we need to do is just to see a pair of training examples at a time, and assume that any point on a path between two training examples lies on the data manifold. So we pick a random pair of training examples, and then we look at a path that's going to connect these two examples, and we pick any one point in this path, and then that point is going to be assumed to be on the manifold. And then that is how we're going to create all these perturbed or the augmented training examples. Now, obviously, you can say that, well, what is that path, right? You have to ask that question, because we have to, or we feel like we have to choose a path that's going to be meaningful in a sense that the path that goes through, that path that connects these two examples by passing only over the data manifold. And that feels pretty much clueless. However, it turned out that when it exists, linear interpolation, simple linear interpolation works really well. And then why is that the case? Because you notice that if we can actually, if we actually consider all possible pairs and then all possible linear interpolation, is very much likely that that's going to cover the actual true data manifold as well. So what that means is that we don't really need the interpolation function between two examples that are perfectly on the data manifold, as long as the collection of all those linear interpolation or the linear segments that we consider cover a large portion of the true data manifold. And then that was actually surprising and turned out to be extremely effective in many domains where we can define very straightforwardly or the trivially linear interpolation between any pair of training examples. An example would be image processing, where we take the two images, they are largely continuous, so we are literally going to mix them in little by little by taking the weighted sum of these two images pixel-wise, pixel by pixel. We can do a similar thing with a speech. We're going to do the mixing either at the spectral domain or at the spatial domain directly. Again, pixel by pixel, as in the time by time or the frequency by frequency. So that's great. But unfortunately, there are many domains such as natural language where such a trivial linear interpolation is not there, or we are not aware of such one. So this is where our idea of, can we then train a language model to learn to interpolate in natural language processing so that we can use it for non-local data augmentation. This is a collaboration with the research scientists from Hyundai Motors, Ye-kyung and Seohyung. So then, in order to think about it, we need to think about the generative learning from the scratch. So what is generative learning? So the generative model M is we train generative model on a set of data points where the data point refers to only the example from the input. So we don't have a paired data, but just data without any labels, so unlabeled data. And once we train it, however we train it, we can now draw, we should be able to draw a sample from the model M, this model. And then this drawn sample, or the sample that were drawn from this distribution, should look very, very similar, but not exactly as the training examples. Now, that's very important, what I just said, because that is the definition of what we mean by generalization in generative learning. In the case of classification, generalization is a bit easier to imagine. So here's a new example, input example, and my classifier should be able to classify it correctly. That's going to be generalization. But in the case of generative learning, generative modeling, generalization is a bit less trivial to think about. But then what I just told you all just now is exactly how we should think about it. We are going to draw samples from this generative model M that has been trained on a finite number of training examples. And then these samples that were drawn from this generative model shouldn't be one of the training examples, because that's going to be a symptom of overfitting. But still, they need to look very, very similar to some of these training examples in the training set. And if you think about these two criteria for determining whether a generative model is generalizing well or not, we notice that this actually does sound like what we would mean by interpolation of all those training examples. In other words, generative modeling is in fact how to learn to interpolate all those, let's say, training examples that are not labeled. And we're going to have this as a foundation on top of which we build a language model that learns to interpolate very, very explicitly. And you can imagine that because of all those popularity of the meta learning as well as learning to learn, you can imagine that we can, if we think of generative learning as equivalent to learning to interpolate, then we can think of it as trying to build a machine or algorithm A that's going to map from an existing set of training examples into an interpolation distribution from which we can sample a interpolated version of all these finite number of training examples. That is, our input is now going to be the training examples, and then our algorithm A is going to give us an interpolation distribution. And if we think of an extreme case where we only have 2 examples only, then this algorithm A takes as input 2 examples, and then the interpolation ratio, lambda, and it outputs a distribution over the input space such that the probability is high on the points in the input space that is similar to both x1 and x2. However, that point is not going to be exactly like either of the x1 or x2. So this machine A, algorithm A, is going to suddenly become an interpolation machine because the generative modeling is precisely learning to interpolate. And we can now meta learn this algorithm from a large amount of unlabeled data. So let's just think about this interpolation a bit. So let's say I have all these different training points. So let's say red axis. And then I'm going to pick 2 examples from that. And then what should be the interpolation distribution look like? Interpolation distribution should have a large bump on these 2 points, definitely. And then the size of this bump has to be proportional or according to this lambda, the interpolation ratio. And then they have to be regularized so that it's going to be smooth. Why does it have to be smooth? Because otherwise, it's not going to be interpolation, but just choice of one or the other training example, these 2 examples that were given to our algorithm A. Now, how do we train our algorithm A to produce such an interpolation distribution? It turned out that it's as if we're building a very large training set that consists of the x1, many copies of x1 and many copies of x2, those 2 examples, but the number of copies will be according to this lambda, the interpolation parameter. And what happens? We can in fact write down the maximum likelihood learning criterion. That is, given x1, x2, and this coefficients lambda, we want to maximize the log probability assigned to x1 itself. And also, we do the same thing for x2. But then we have the radius sum that tells us which one has a higher emphasis in given this lambda value. And we do the meta learning by minimizing this particular loss function or the objective, well, by actually maximizing this objective function over all possible pairs given the training set, the unlabeled training set, very large set, and also over all possible values of this lambda. And then we need to define some prior distribution over lambda. We can use some beta distribution with the parameters alpha and beta to see how they look like. But in some sense, we can only just use a uniform distribution as well. And because computing this entire thing is going to be not feasible or not tractable, so we use stochastic approximation or the stochastic optimization as usual. Now let's look at how this algorithm A that we meta learn look like from the perspective of parametrization. So we are going to use a neural network sequence to sequence model that takes as the input 2 sequences, let's say x1 and x2 or the xa and xb. And then we're going to share one encoder. We're going to use one encoder for each one of them separately to result in this set of vectors for each of the input. And what we do is we introduce a length converter that we use for the non-autoregressive machine translation earlier last year in order to standardize their length according to the weighted sum or the linear interpolation of the length between these two examples. And once we do that, we're going to take the linear interpolation of these hidden vectors for each of the locations separately. And then now it's a linear interpolation in the hidden space, not in the original space. And given this interpolated version, we use a single decoder to decode out both x1 and x2. And then that's how we're going to compute the log probabilities assigned to both x1 and x2 and take the weighted sum in order to compute the objective function. And we train the whole thing end to end. And we often start with the encoder and decoder that were pre-trained as BART on a single sentence reconstruction task. Now, unfortunate thing is that if we simply maximize this objective function as it is without any regularization, it's not really going to do the interpolation because there is a huge degeneracy. That is that the probabilities assigned to x1 and x2 will simply sum to 1, meaning that no other input sequence or the input configuration is going to receive a probability. So this is not going to be interpolation, but selection between these two examples. In order to address this degeneracy, we use 3 different regularization techniques. First one is random masking. This is quite standard these days. Second one is adding noise in the hidden vector space. And then the third one is to try to decay them towards 0. This reminds us of the variational autoencoder, where we try to ensure that the hidden vectors occupy the entire space in our interest. And then this is really necessary for our interpolation scheme to work well, because given any 2 hidden vectors, we're going to try to interpolate between these 2 linearly in this hidden space. So we want this hidden space to be as tightly packed as possible. It turned out that adding all these 3, let's say, regularizer is a way for us to, let's say, address this degeneracy quite effectively. Now, then the question is, can we expect a meaningful interpolation in this scheme? And then what does it even mean for us to meaningfully interpolate between 2, let's say, natural language sentences? Now, I don't really have a rigorous answer to that one, but I do believe that we can trust that meaningful interpolation will arise from this setup or this scheme because we use deep neural networks. Now, let's assume that we kind of are very excited by the success of language generation from these deep neural networks these days. Then what that means is that, in fact, these deep neural nets are indeed very successfully interpolating among all those the large number of training examples that were given to were used to train these deep neural networks. If that is the case, as in if we are indeed amazed by the quality of generation from these large-scale language models, such as GPT-3, and more recently PaLM, as in like the language model from, let's say, 2 days ago from Google, then we should very naturally expect this learning to interpolate to work just as well. Not the most satisfying answer, I understand. However, if we are amazed by the quality of the language generated by language models, then we should be able to trust that this scheme, the learning to interpolate, will produce a meaningful interpolation. So then you have to, okay, does this approach, what we call, let's say, LINDA, learning to interpolate for data augmentation, actually learn to interpolate? So looking at the unigram precision versus, let's say, interpolation coefficient. So we're going to look at whether the generated interpolation overlaps well with the first sentence or the second sentence using the unigram precision. And then we're going to look at that one with respect to the interpolation coefficient. And then what we see is that yes, we do actually see that the unigram precision very smoothly changes as we change the interpolation coefficient. This is very, very, what can I say, very encouraging. And this happens not only on the training domain, that was a Wikipedia, but also on other domains such as the track. It's not T-RED, but the track. And let's look at some of the examples, because at the end of the day, because we cannot really quantify the meaningfulness of interpolation, we have to just look at them a lot and then see, whether meaningful interpolation is actually happening. So here are some good examples with the extreme interpolation. That is that the interpolation coefficient lambda was set to be 0.5 or close to 0.5. Let's look at the first one. Relaxed in his perfect quiet place and proud in his message. That was the input one. And then the second input was the plot is both contrived and cliched. That's the second input. And then we asked Linda to interpolate between these two examples with the interpolation coefficient of 0.5. And then what it produces is this. The plot is both perfect and cliched in its message. And then we do see that some of the phrases and some of the words from both of these sentences were mixed in. However, they were mixed in a way that produces a very well-formed sentence. And then we do see this kind of example very, very easily. The second example is something like that. And then what we do see is not just a mixing of the words. It actually does a lot of the paraphrasing as well on its own. And furthermore, what we see is that Linda actually learns to interpolate or to mix in both the semantics as well as the syntactic features. So this is an interesting example. The first, the generated interpolation in terms of meaning is very much skewed toward the first input. However, if you look at how the generated sentence is written like, it actually looks, not the meaning, but it looks very much like the second input, having a lot of, let's say, periods after saying anything. So it really does a mix of not only the words, not only the semantics, not only the syntax, but everything at the same time. Now, of course, there are some bad examples as well. And it's just bad example that you see from any kind of language model that we train is that it does hallucinate. In particular, when the original sentences were out of the training domain, the Linda was found to hallucinate more, especially with the coefficient that is close to 0.5. As you see on the slide, the input sentences have absolutely no information about the date or the place where the film was released. However, Linda just makes it up. It says that the film was released in the United States on October 2nd, 2019, and in Canada on October 3rd, 2019. Very plausible, but has nothing to do with the input sentences, which makes it not really an interpolation at all. So we tried it for the actual data augmentation by using it as a way to generate all those mixed examples given any pair of the training examples. And similarly to Simba that I presented earlier, it does improve upon the baseline. And it almost never it hurts the accuracy. What that means is that we are generating all those examples along the data manifold. And then the fact that it is working as well as, or actually often better than Simba, tells us that indeed this is a better way to explore a larger portion of the data manifold. And then it happens across all these data sets that we have tried, and there are more experiments and results in the paper, and the paper is on arXiv at the moment. So this is a novel strategy for learning to interpolate. And then this is a kind of, let's say, one small step that we have taken toward domain-agnostic, non-local data augmentation. The community, machine learning as well as the NLP communities have already known how to do non-local data augmentation, but those methods had to be very domain-specific. We have known how to do domain-specific data augmentation, but they tended to be very, very local. But now we know how to do domain-agnostic, non-local data augmentation, and then there are a lot of things we can do further. So there is one final part, but I think I'm running out of the time, but I'm going to quickly go over it. So we wanted to answer this question that I think we should have answered much earlier. That is that does the relationship between the manifold assumption and generalization actually hold? So if you recall, I actually said earlier that if we have a smoother classifier that is smoother over the data manifold, it's going to generalize better along the data manifold. But is this true? I mean, that's a big assumption that we have in statistical learning theory in general, but is this really true in the real world problem that we're trying to solve? And then does it hold, especially if we characterize or capture this data manifold or the user data manifold captured by unsupervised learning? So we really should have actually answered this question from the beginning. We already have an indirect answer. And then that indirect answer comes from the fact that we can use this kind of idea to do the data augmentation and get a classifier that generalizes better. But we wanted to see really directly whether this is true. So what we did was to essentially to define what we call smoothness measure on given a classifier and the target domain data. So we are going to be given some set of test examples that were collected from some distribution. And then we're going to be given a classifier. And then our goal is to see how smooth this classifier is in the data manifold defined by this target data set. How do we know the data manifold? We're going to use Simba. We're going to use masked language model, or we're going to use EDA, or whatever the data augmentation methods that capture this local data manifold structure to check or to capture the data manifold defined by this the test set we are given. And then we check how smooth our classifier is over the data manifold. And then smoother the classifier, we would expect the better the generalization accuracy is. And we actually did check it directly in order to answer this question. Is the relationship between the manifold smoothness and generalization true? And because I'm running out of time, I'm going to go quickly. And then, of course, it's not an absolute measure, it's a relative measure. So we had to create several thousands of the classifiers that were well trained to a certain degree, but resulting in a different levels of the generalization accuracy by using different, let's say, regularization techniques as well as the various noise schemes. And then we see whether we can order all these classifiers correctly according to their generalization accuracies without knowing the actual labels in the target domain or on the target set. And we tested various ways to capture the data manifold. Of course, Simba is the one that we talked about at the very beginning. EDA is another one that is very much domain specific methods. And back translation, BT is the round trip translation. We also tried just a random replacement some of the tokens. And we compared against, oops, sorry about that. My apologies. I guess there is some kind of construction in the apartment above. Yes, that's unfortunate. I'll just try to say, speak loudly.
Yeah, speak loudly. I think we can hear you okay.
Yes, sorry about that. And we also compare against a manifold agnostic baselines as well. And then those are the All right, okay. So we also test the manifold agnostic baselines, which is average threshold confidence that was proposed only this year, very early this year. And then using two different criteria, negative entropy as well as a maximum confidence. Let's see. And then what we saw was that this R2 that actually tells us about how well these two metrics correlate with each other. So can we really sort these models according to generalization accuracy without knowing generalization accuracy using the smoothness over the manifold? It turned out that it's extremely high. We can really sort all these models according to how well they're going to generalize without knowing the target labels. And then we could see that this actually works in the extreme out of domain case as well. So we look at the drug reviews from drugs.com, and then we could still sort all these classifiers according to their generalization accuracy. And then we made a lot of similar observations on natural language inference as well as the other data sets. And then there are more experiments and results in the paper. However, this paper is still not on arXiv. So if you just drop me an email, I'll be happy to actually share the manuscript with you. And we did some further analysis on sensitivity, such as if we use more examples, can we predict the generalization better? Turned out that the answer is yes. And then it turned out we actually don't need too many neighboring samples for each of the test example in order to identify the local data manifold. Now, of course, this may tell us more about the data manifold than the smoothness metric. So yeah, it turned out that our original assumption or the motivation was indeed quite correct, and then it is applicable to the real world problem as well. But unfortunately, it's not a magic bullet. It requires unlabeled examples to cover the target domain. And if you don't have enough, let's say, unlabeled examples to cover the target domain, of course, it's not going to work. What that means is that we are really looking into the data-driven approach to identify or to characterize this data manifold. And then we're trying to see what happens to classifier in some small portion of the data manifold that we have been able to capture. And it does reorient our view of the generalization, is that the generalization is a function of a classifier as well as a target region of interest over this data manifold. But anyway, so final slide, I promise. There are still a lot of remaining questions. Most of the experiments here were done for natural language processing. How general are these observations and conclusions beyond natural language processing? We do have some, let's say, experimental evidence that many of these algorithms actually do work beyond natural language processing, for instance, for the object recognition and whatnot. And second question that I think is important is that the unsupervised learning does capture data manifold, as we have seen, but how does it connect to its effectiveness as a primary initializer? Very difficult question, but there has to be some connection between the initialization or the effective pre-training method for fine-tuning and the training to generate all those examples or the characterizing the data manifold. But this relationship is not easy to characterize yet. We need to do so in the future. And then the final question I think is really interesting is that can we actually use this method that we have used for the data augmentation to do a better active learning? So instead of waiting for each of the examples to arrive in online way, can we actually make it very active? That is, can we use these methods to figure out what are the examples that we want the labels for, rather than just saying that, for any given example, do we want a label? And then that's going to be somewhat like active learning. But it is unclear what is the right way to go about, and then I think the further research is needed. And with these remaining questions, I'm going to wrap up my talk. And if you have any questions, I'll be happy to answer any questions. Thank you for your attention. And my apologies for the construction in the apartment. I'm sorry. The upstairs neighbor is like this. They go crazy of all those construction and the woodwork and so on. But sorry about that. I hope it's not too disturbing to you.
Do we have some questions for Kyunghyun Cho? I was thinking a little bit about Linda and sort of when you started talking about the semantics and the lexicographics there. It sounds like most of what you're evaluating here is lexicographic, like you have overlaps in unigrams. And you showed one example of sort of semantical sort of overlap. But is this generally so in the evaluation? Do you see the semantics in the generated sentences?
Yeah, so these examples weren't too difficult to find, in a sense that most of the examples that we get do have this kind of some mix of, as you said, some lexical mix, the syntactic mix, semantic mix, and we do see a lot of them. Now, unfortunately, it's not really easy for us to quantify, what is the proportion of that happening, because we don't really know how to measure the similarity in terms of the semantics or syntax as well as we want them to be, right? So only kind of, let's say, way for us to tell was to look at a lot of these generated examples and also just plug it in the data augmentation pipeline. So trying to see if our assumption is that if the examples are not mixed well enough between these two examples, then our assumption is that it wouldn't help at all in terms of classification. And then, of course, indeed, the improvement is not too big, but still, we were able to see that it always helps. It never hurts. And then I think that is one kind of, let's say, good indication that it is doing a meaningful interpolation. However, I have to say, we thought it's going to work better in terms of the more dramatic, let's say, interpolation, but it didn't, which means that we probably can come up with a better parametrization as well as a better regularization, in addition to the loss function that we have defined here in the future.
Thank you, Kyunghyun, for this inspiring talk. Next week, we actually have Easter break, so there's no seminar. So in 2 weeks, we have the next seminar, which is Jacob Swart from the US Geological Survey, talking about stream temperature forecasts using process-guided deep learning and data assimilation in support of management decisions. Right. Thank you very much for today.
Well, thank you for the invitation. It was fun. Bye-bye.
Thanks.